Hello, everyone. Today we will be talking about delay, or it's also called dead time. Now, until this point, we've considered that if a input is applied to a system, that the system directly shows an action and reacts to it instantaneously. Now, of course, that's not always the case. Sometimes, and most of the time, it's more about the sensors in a feedback loop that need some computation time and then react to the then basically react and give you some measurements. An example for that would be, of course, an autonomous electrical car, which would use computer vision in order to sense its environment and send some feedback data. And of course, that also needs some computation time. That could be some delay. Or for trains and high-speed trains, if one wants to activate the brake on such a system, then it takes some time to get the right pressure and then to be able to apply the brake. So there's also some delay. There are electronic component delays which are in nanoseconds, which we actually don't even consider most of the time. But there are systems with delays, and it is important to take them into consideration when we analyze a system or when we are trying to synthesize some controllers. We should be aware of the delay or dead time. Now, of course, this is an important concept because when it's like more than 0.2 seconds, more than 0.1 seconds, we can basically say that it's not instantaneous. Therefore, it takes some time to measure that or to get some response out of the system. In this case, we are looking at a 2 seconds delay on a certain given system. Now, in the time domain, defining delay or the dead time is not quite that problematic because it takes a tau amount of time to react. So therefore, when the system has delay in it, what we can do instead of yt, we can represent that as yt minus tau. And when t minus tau is positive, we have a certain output. So at t equals tau, we kind of react. So therefore, we can model the delay with a subtraction or shift in the time axis. If you look up this property, time shifting property, for the Laplace domain, the Laplace transformation of this time shift actually corresponds to the e to the power of minus tau s. So therefore, you can see that when we have transfer functions where delay or dead time is involved, you will get basically e to the power of something times s. And this will basically tell you how much delay the system has or dead time the system has. In our case, we have this 2 seconds of delay. And yeah, this will actually cause some trouble because something is simple in the time domain, then probably it will be a little bit difficult in the Laplace domain because vice versa holds. Consider the basically the convolution in the time domain. When you have convolution in Laplace domain, you're just going to multiply them. So when something is difficult on the other domain, it is probably going to be easy or vice versa. So in our case, this is a bit of a problem when we have this 2 seconds of delay. And let me demonstrate to you what the problem actually is. Because we have a system that has gain 12 and the poles are at 4 and 6, I can define a system like this. And what we can do is we can separate this, but before I separate them, let me just show you how I define a system with delay. Now, on top of the poles and zeros, what we do is we basically add a property which is called IO delay. So there's a possibility of having delay between like internal states and input or internal states and output. But the delay that we're adding here is between the input and output because it's using a transfer function. So it would make sense like that. So we have 2 seconds of delay. So the only thing that we need to do is we need to add this property IO delay and give it the amount of delay 2 seconds. Now, if you have such a system, and let's just come up with an arbitrary controller. Let's have API controller, for example. For some reason, this is going to be the controller. And when we have the feedback, let's see what happens. Now, this is GS, and you can see that MATLAB also use the same notation because it has to. In the Laplace domain, it will be e to the power of minus 2s, 2 being the delay here. Now, let's have the controller, s plus 1 divided by s. This is the PI controller that I came up with. And let's have TS. Now, for some reason, the control system toolbox actually converts this into a state space representation. And as always, what I'm trying to do is I'm trying to look for a transfer function. And when I enter it, it causes me some error and says that we have some internal delays that cannot be converted into transfer function form. So interestingly, even if we start with a system that has delay in it and is a transfer function representation, and even if the controller is also in a TF object, the feedback seems to be something different because MATLAB is not able to, or the control system toolbox is not able to convert this into a transfer function representation. What you might have expected from this is that you might have expected a transfer function times some delay, probably the same delay, because why would it change if I have a feedback loop? So it seems like that's not possible. So this is a bit concerning. Let's actually try to use a bit more powerful tool that we have, which is going to be basically the symbolic toolbox. Let's try this again. Now, GSS is going to be 12 divided by s plus 4 times s plus 6 times exp minus 2 times s. And then FSS, which is 1 plus 1 divided by s. And then TSS is going to be FSS times GSS divided by 1 plus FSS times GSS. So my motivation here is that I don't really get the idea where the control system toolbox is not able to give me a transfer function form, because all it has to do is it should just multiply them, use this formula here, and show me something that is similar to a transfer function and some delay probably. Why isn't it possible? So I'm trying to use basically the symbolic toolbox and repeat the stuff symbolically. So let's see what the outcome is going to be. And there we go. This is basically the result of our calculation. Now, you can see that some terms in the denominator will have e to the power of 2s in them, and some will not have them. And it's obvious why we will have this, because, ns plus ns times the numerator of the controller, which is s plus 1, plus s times ds. And then, of course, ns has this exponential term here. So what we can do is we can separate out the e to the power of 2s portion here. Let me see. We have that in s cubed and 10s squared and up to here. So if we divide everything into e to the power of 2s, what we will get is we will get basically s plus 1 times 12 times e to the power of minus 2s, and then s cubed plus 10s squared plus 24s plus e to the power of minus 2s, 12s plus 12. That's going to be it. And yeah, since we have this nonlinear term in the denominator, and if we factor out, it will be on both the denominator and the numerator, it is kind of obvious that these are now no linear terms anymore, these cannot be called polynomials. And since we define a transfer function, a ratio of polynomials, it makes sense that MATLAB complains about the fact that this is not a transfer function form anymore. And it isn't. Because it should be the linear combination of the powers of S in the numerator and in the denominator. And we don't have that here. So that's an issue because all that we know to do is we know how to work with poles and zeros. We have dominant pole assignment. And all we care about is to try to force two poles on a certain region, and we try to place all the remaining poles and zeros out of the dominant region, and we try to therefore conquer a system's behavior by doing that. But here we don't have a polynomial, therefore we are not able to have or calculate some poles and zeros, so we're in a bit of trouble. And that's the reason why we have this lesson, of course, today, because we need to deal with this e to the power of minus 2s. This is a nonlinear term. If you have a feedback loop, then you're in a bit of a trouble. Without a feedback loop, you're not that big you're not in a big trouble, because we can basically shift the non-delay part by 2 seconds, and that will be the response. So let's actually do that. So let's have a figure, and let's calculate the step response. Now I want to separate them to be able to have a delay part and a non-delay part. So all that I'm going to do is I'm going to have a unit transfer function, which is just the scalar 1 divided by 1 times I delay. So this is pure delay, and this is the system. When I multiply them, I will have the system with delay. If I don't, then I will have actually the system on its own. So let's have the step response of GS. Plot that. There we go. Now let's multiply that with GD, and let's plot that too. Let's have hold on, grid on, time, step response. Let's give it a 8-second time, maybe the same time vector. There we go. Now, as you can see, the black response here is basically the system's behavior, and it is expected to have this because we have two real roots, 4 and 6, and therefore it's going to be 12 divided by 24, which is 0.5 in the steady state. You can see the overall value is 0.5, and it has a certain setting time value, which we cannot really calculate because we don't have the setting time formula for that. But yeah, we can see if it would have been 4, then 4 divided by 4 would be 1, so it's a bit slower than that. And so on and so forth. We can see that the response here makes sense. And when we add delay to the system, which is an IO delay, we can see that for 2 seconds, the system doesn't respond, doesn't react, but after that, it just reacts as it would be without delay. So we did really shift it in the time axis by 2 seconds, and that is no big deal. But if we have a feedback loop and place such a system in a feedback loop, then somehow the closed loop is not a transfer function anymore. And that is it that we have up to this point. So how are we going to deal with this? Now, you might think about using the Taylor expansion or some sort of an expansion, because we have a nonlinear term. We might want to approximate that with linear terms. Then we would plug that in and we would have a transfer function. It is possible to do that, but there's a better way of dealing with this. And it is almost something like the Taylor series, but it is a bit more special and a bit more different than that. Namely, it is called the Putty approximation. And what it does is it kind of approximates this e to the power of minus 2s with a transfer function, which is exactly what we're looking for. Because, first of all, we have a stable transfer function here. This is the first order approximation, which you get here. And in the Taylor series, you might end up in unstable approximations, which you wouldn't have, which you wouldn't like to have. So that might cause some issues. But here we can see this is a special approximation method, and we will see how it is working and why it is working actually in a minute. What it does for the first order Putty approximation is that it places a pole at a certain place and a 0 on the right half plane symmetrically. So there's a certain symmetry to it because the second order transfer function is given here, the first order is given here, and the general form is also available, but I didn't put it here in the PDF. But in the general form, there's also this symmetry there. So what we are going to do is we are just going to replace this e to the power of minus 2s with this transfer function, and then you're good to go. You're good to go because when you have a transfer function, you already know how to deal with that in terms of stability, in terms of controller design. We're used to that. And it is quite important that we have a method where we can replace this and get a transfer function that we can deal with. Of course, there will be a drawback because this is an approximation. We need to be careful, but first of all, we are going to deal with it. So that's nice. Of course, the higher the order of the approximation is, the higher the accuracy will be. So you would like to have the highest order Putty approximation if possible. So let's actually see how the step response, for example, of this first order approximation of the system looks like. Now, let's call it GS1. It's going to be GS times TF. And let me define tau equals 2, the amount of delay. And there we go. So 0.5 times tau s plus 1, and then minus 0.5 tau s plus 1. Let's also have GS2, which uses tau square divided by 12 s square. So the same goes for here. And there we go. Let's start with the first approximation here. Let's use a red color and let's see what's going to happen. Now, it is nice to have a transfer function. It is nice to be able to plot the step response. But something that is not nice for this approximation is that the approximation itself, it doesn't seem to be trying to be even similar to the original system with delay, because that's the blue one, and we want to approximate that one. But it doesn't seem like it because, well, first of all, we have a undershoot here, and then we have the transient part here. And the only thing that matches is basically the steady state value, and that's it. Now, what about the second order one before I talk about it? Let me show you the second order approximation. Let's choose, I don't know, we have blue and that. Let's choose magenta. And there we go. Now, it seems like the second order approximation is also not that similar, but has a little bit more to it than the red one, because at least we are basically reaching it before the red one reaches the actual response. But in terms of approximation, both seem to be terrible. Now, what is it that this approximation tries to accomplish? If you think about it, the system does not react for 2 seconds and then starts to react and has a certain transient to it. Now, the red one here actually reacts because when we have a transfer function, if there's no delay or dead time in it, it will instantaneously react. There's no getting away from that. And even if it's an approximation, we will react because the system has no dead time at all. And we're approximating a dead time system with a system that doesn't have dead time. So the best it can do is to waste some time. So it has undershoot, it goes like this, and it returns to the point where it started, basically 0. So therefore we have a 0 crossing at this exact point, which is approximately 1.1 seconds here. So I could assume that the red one here has 1.1 seconds of delay or dead time because we started from 0, wasted some time, and returned to 0. And now we're starting to react in the right direction. Now, if you look at the magenta one, which is a singular approximation, then we go upwards now, up to 0.1, and then we return to 0. This is the first part where we wasted some time in terms of delay. And then we have undershoot, where we waste a little bit more time, and we reach 1.55. Now, the magenta one, the singular approximation, has 1.55 seconds approximately, and models the settling time, the dead time, only with 1.55. If we would be able to do this a little bit better and waste exactly 2 seconds, we would be at least correct in terms of delay. Now you can see that the delay or dead time model with the approximation for the first order or second order is not perfect and not even near perfect. So what are we going to do is, we're going to basically look at higher order approximations because, well, these two don't look that promising. So instead of doing this on my own, I can basically ask MATLAB to do this because the first 2 orders are quite obvious. I did use the approximation transfer function directly, but what I can do is I can use the PuTTY command, which is available here, and give it the delay or anything with delay. I'm just giving the pure delay, but you don't really have to do that. You can also give it GS times G delay here. And then the order. Let's try 3, for example. And we are going to use this PuTTY approximation and plot this. So what we can also do in order to see what's really going on here is we could add the pole 0 map to it. So let's call this AX1 equals CCA AX1 AX1. So let's have the second one. Pole 0 map. And then also the zeros. There we go. Now let's look actually at the first order approximation back again. We should add this to this one here. It should be X2. There we go. Yeah, let's also maybe add an S grid here. X2, zeta, let's choose that. 1 up to, I don't know, 6 to show the S domain here. So now, first of all, we see that we have a 0 on the right half plane, and then we have a pole on the left half plane, and the pole is at -1, the 0 is at 1, so it has a symmetry to it, and this is the result. Now let's increase the order to 2, the second order approximation. We can see now the strategy is a bit different. We have basically a pole pair on the left half plane and a 0 pair on the right half plane, which are still symmetric. And let's try the third order one. Now you can see we have an undershoot, an overshoot, and then again an undershoot, and we're getting closer to it. The third order looks more promising because it almost wastes exactly 1.73 seconds, which is almost 2 seconds. So the delay part gets improved. And then you can see that the transients start to pick up here, and it becomes more familiar. And when it's the third order one, we have 3 poles and 3 zeros. So I'm going to do something like AX2 and then equal, as far as I remember. If I do that, you can see, of course, it is symmetric, and it's kind of on a circle that has a certain radius, namely 2.33, 32, something like that. So it's kind of on a circle. Let's increase it furthermore. You can see now we have 4 zeros and 4 poles, and then we have 4 crossings. So 1, 2, 3, 4, 4 times we are crossing the 0 axis here, and the transient parts are even more promising. And this goes on like this. So fifth order, and then let's jump a little bit. Let's have the 10th order approximation. You can see now that at a certain point, we are matching the transients as they are, but you can also see that when we increase the order of the approximation, the peaks are getting lower and lower in amplitude. So what happens when we have the 20th order Putty approximation? At some point, you can see that it is constantly wasting time around 0 with small peaks. And practically, this could be used as the original system because we will have noise. If I add noise to it, you won't even recognize this part here. And then when the system starts, you will pick that point and say, okay, there are 2 seconds of delay. There's a 2-second of delay, and that's basically it. So practically, we don't really have to improve upon this, but we can go on as we wish. So 40th order approximation, if that's still usable, you can see visually it's not different anymore. But of course, we have too many zeros and too many poles on the left half plane, namely 40 zeros and 40 poles from the approximation and 2 poles of the system. We're basically having a nightmare here because GS Putty is something that we wouldn't like to have. It's not even fitting here. And you can see this is a very bad transfer function to deal with because, well, if you're looking for stability interval, you could cope with this. That's not that big of a deal. But if you're trying to design a PID controller, you should be not using this approximation because that's quite painful. Yeah, I don't know if we would do something like this for PID design, and it doesn't even matter. Does it even matter? That's the question. For the step response in open loop, we have a perfect matching transfer function, which still has these this wasting time around 0. It's still there, but it's neglectable at this point. But we have too many poles and zeros in our model, and I wouldn't like to work with such a system. So, of course, even the third order or fourth order approximations are quite difficult to deal with because we have too many poles and zeros. As you can see, 3 zeros and 5 poles are still a nightmare. So that's still too much for a PID controller design. And yeah, so our strategy is going to be the following. We want to have high accuracy, but we also want to have a simpler design problem. So the best thing to do here is by starting with a first order PuTTY approximation, trying to design or analyze the system, and then see if that's enough. If it's enough, we can leave it at that. If not, we could then increase the order of the approximation by 1 and try it again. If it's still not satisfying, then increase it by 1, increase it by 1 until you are satisfied by the results. Of course, from 3 and upwards, I'm not sure if we will use the PuTTY approximation with that high order. If you are interested in it, try dealing with a third order, fourth order PuTTY approximation. So now we see how or what the method here is. We're basically using the right half zeros, namely the undershoots, in order to waste time around the zero axis. And then we're trying to basically add them together with small peaks so that we end up in having the exact same response. So this is a special approximation that is used for delay. So when we have a system with delay, one thing is that we can replace the delay portion with a PuTTY approximation and start trying to design or analyze the system. So let's actually try to come up with the p-type controller interval for our system with delay. We've seen that we can basically go with higher order PuTTY approximations like 40. And this also shows the fact that when we have this e to the power of minus 2s, we actually have infinite amount of zeros and infinite amount of poles. Because this approximation tends to infinity, it's a series expansion, and it would be basically e to the power of minus 2s. So we can conclude that the system with delay has infinite amount of poles and zeros. Therefore, it's not possible to, for example, plot a root locus plot because it doesn't have finite amount of poles and zeros. The first step of a root locus plot is to place the poles and zeros of the system. But if there are infinite amount of them, how can I place them? And the best thing is, again, the closest thing that we can do is just use the PuTTY approximation. So let's actually use this. Where do we have it? There we go. Now let's start with the first order PuTTY approximation, and yeah, let me just take this one here. Maybe leave it at 2. I don't know. So let's look at the stability. Now, of course, what we are going to do is we are going to use the PuTTY approximation itself. That's a transfer function, so I can convert it into TF to sim, which I've added for simplicity. You can convert this into a symbolic one, and then we are going to define K, and we're going to look at the closed loop, K times GSS divided by +1, and then the numerator, denominator equals num then GSS, and then we need omega. P omega is going to be substitute PCS as 1i times omega, and then problem is to solve for the real part of P omega should be 0, and the imaginary part P omega should also be 0. So let's see. Of course, we need S. Let's place it here. There we go. Now we have 3 values. I'm going to convert them into double. Same goes for omega. Now I'm going to eliminate the ones that are not 0 or positive. So omega should be positive. It can be 0, so k-val is going to be k-val. Index. Same goes for omega. So I'm going to display k, display k-val, omega, omega val. There we go. Now we can see that the interval using the first order Putty approximation seems to be -2 and 2.43, and omega is 0, so this is a negative crossing, origin crossing, negative root locus origin crossing, and this one is a positive root locus crossing here. So what we can basically do is we can plot the we can plot the root locus plots. So R locus of GS Putty, which is basically the positive root locus, and we know that it is 2.43. So only the poles are important. So poles are PZ map feedback times GS Putty, comma 1, plot real poles, and then imaginary poles. Like this. Or we can also do it for the negative root locus, which is going to be negative, which was -2. And there we go. So now this is the figure, the resulting figure here. And we've basically calculated these j omega crossings on the positive root locus or this origin crossing on the negative root locus. Now, is this the stability interval of the actual system? Now, that's a big question here because we are using an approximation, and how are we going to rely on this? Is it reliable? Because it's an approximation, and we've seen, or we are still seeing it, that we did use the first order one, and even the second order one was not capturing the behavior of the system. So is it reliable? And of course it's not. So when you use the Putty approximation and you come up with an interval, you cannot claim that the system will be stable in that interval. But you can claim something else, which is quite interesting to note. You can basically claim the instability interval. So what I mean by that is that if the Putty approximation is stable in this interval, out of this interval, it's not going to be stable. And the system is also not going to be stable for sure. So between -infinity and -2, the original system is also not stable. Between 2.43 and infinity, the original system is also not stable. It could be stable at 2.43. It could be unstable. But this is basically a upper bound on the actual stability interval. We can only say that this will be an upper bound. And it doesn't necessarily mean that if the Putty approximation is stable, that the original system with delay should be stable, because you can see the step response does not even look similar. So it's not capturing all the dynamics, so I cannot claim that. But I can claim that greater values than 2.43 will cause instability for sure. So that's a nice thing to add here. So it means that also when I increase the order of approximation, this will change. So keep in mind that this is 2.43. So if I run it again, first of all, I get more points here. You can see that the positive root locus did change. Now we have a crossing that looks like this. On the negative one, we have a crossing at the origin and on the j omega axis. But we can see that the more conservative value is again -2, so -2 is good. But now it's 2.16. Now, this body approximation tells me that between 2.16 and 2.43, the actual system is still unstable. That's why I'm telling you that this interval tells me where the system is not stable instead of telling me if it's stable in that interval. So outside of 2.16, now I have narrowed it down a little bit more. I can see that from 2.16 up to infinity, the original system should be unstable. Between -infinity and -2, the system should be unstable. So we are capturing that part. That's no problem. The origin crossing here is quite accurate, but the crossing on j omega axis is not. So the positive crossing is not accurate. So this is still an overbound. So let me increase it one more. Let's have 3, for example. And I get even more candidate points here. Now we have 2 crossings here and 3 crossings here. And I can see that between -2 and 2.15 now instead of 16. So I can see that it is somewhere around 2.14 or 1.5. So these digits will become stable in a moment. So let me increase it again. 2.15 seems to be the 2 digits here. I'm not sure about 32, but if I go ahead and increase it even more, now MATLAB solve methods becomes unreliable. So what we can do about that is we can change it to VPA solve, which is a numerical solver. Now we get the candidate points now. You can see we are getting more and more points of j omega crossing here. And of course, now this algorithm here is not correct. This is not showing the correct thing here. What we can do is we can have a small for loop here from I up to length k val. And what I can do is I can check for if k val index I is positive. If it's positive, I'm going to use k val I. Now I'm going to repeat this for here. Now, if it's a negative value, then I'm interested in a k-val index, basically I, and that's more correct, I guess. There we go. Now you can see we have more and more crossings, and it becomes out of control, but we can still deal with that because that's not that big of an issue. Since the order goes up, it's becoming more and more crazier. But you can see all the crossings are marked here and also here. And we can see 2.1531 is kind of now the upper bound, and the system should be stable between -2 and 2.1531. Yeah, it is important to note, and it is very important to note, actually, it's a crucial information that we should view this Putty approximation like we view the Fourier transform or Laplace transform. What I mean by that is the following. This is an approximation, and what we're doing is we are taking the system with delay. Instead of dealing with that, we are converting this into its Putty approximation. We're moving the problem from the real world to the Putty world, let's say. And we're trying to attack the problem in the Putty domain or world. Once we're done with that, what we have to do is we have to actually convert this back into the real world. So when you use the Laplace transform, let's say you want to calculate the step response of a certain system. What you do is you convert the transfer function or the system into its transfer function representation in the Laplace domain. You solve that problem in the Laplace domain, and then you take the inverse of that, which is basically you go back to the real-time world and check if it's correct or not. You should do the same with the Putty approximation. Never, ever, ever use the Putty approximation transfer function in any Simulink or in any step response or linear simulation command whatsoever, because it doesn't exist. There's no system that is the Putty approximation itself, because it's an imaginary representation that is a transfer function, and that is all it is. You will use that for stability analysis. You will use that for controller synthesis. You will use it for all kinds of things except simulation. So applying step to this Putty approximation doesn't make sense. Coming up with a controller, we will do that in a minute. Plugging it to the Putty approximation doesn't make sense. You should go to the original system with delay and do whatever you want with it instead of the Putty approximation. So this is a temporary transfer function that you will get rid of eventually, and you will test everything, validate everything on the actual system with delay. Because this is an approximation and it is temporary, we're dealing with this system and this system only. When you have a result, calculate that result based on this system and this system only. For the controller synthesis, we are going to use the step response of the Putty approximation, and we are going to compare that with the step response of the actual system, and we'll see if it's representing it enough. If it is enough, and if it satisfies us, then we will leave the problem. We've solved the problem. We will terminate the problem. If they are not that similar, then we will conclude that we need to increase the order of approximation of the Putty approximation, because it should capture all the dynamics of the system. And if it doesn't, then we have to increase the approximation for accuracy. But other than that, the step response of any Putty approximation doesn't mean anything. So if you have a controller, if you have a stability interval, you should test that on this one here. For root locus plots, you can use Putty approximation because you cannot plot the root locus of the actual system. Wherever you see something that is missing about the original system, you can just use the Putty approximation. That's okay. But if you are looking at the closed loop step response, that should be the original system. So, having made that important, crucial announcement, let's move on. Now, we've seen how to deal with the stability interval because, well, we know already how to deal with that if we have a proper transfer function. And the only thing that we did here is we converted into its approximation, which is a transfer function, and we can deal with that. We did analyze the stability interval. And of course, I've told you, and you should basically try the value 2.1531. You should use that and the system and look at the closed loop if it's marginal stable or not, in order to check if it's correct or not. For -2, you should get a ramp response. For 2.1531, you should get a nice sinusoidal wave, which shouldn't increase, which shouldn't decrease, which should be zeta 0, oscillating forever. So let's design a PI controller, and as you might expect it, we will just use the Putty approximation. It is going to be a proper transfer function. At that point, you can just apply any methods of solving that you want to do. So let's design actually a PI controller with 10% overshoot. So let's define overshoot. Let's calculate zeta. And yeah, we don't know what omega n should be. Well, Let's have it symbolic for now. Let's see. TDS is going to be s squared plus 2 times zeta times omega n times s. This is basically the usual stuff. And we will need, I guess, 2. Because the system is a third order system, the Putty approximation will add 1 to it. Oh, it's a second order one. The Putty approximation will add 1 more. It will be a third order. And the PI controller will add another one. So it will be a fourth order. 2 of them will be decided based on zeta and omega n. And there are 2 residue poles now. Keep in mind that when we use GS Putty, and let me just get it back here. It's a 6th order, so it's a bit of an overkill. So let's use the first order approximation because it's the easiest one. We start out with that. So here's Putty. Now you can see there's a negative sign here. So for the Putty approximations, you should be careful when you're using basically the characteristic polynomial. Now I'm going to convert it into GSS, TF to SIM, GS Putty, and then I'm using KPKI because I'm trying to design a PI controller. There we go. And then the closed loop is going to be like this, and then PZS, PCS, norm then PSS. Now at this point, I'm going to use coef, which is going to be coefs of PCS as all. I'm going to normalize that because I know that it could have a negative coefficient there. Then the problem becomes coef equals coefs of PDS times PS as all. Before we solve it, let's display it. There we go. So let's run it. Now, we have omega n, we have A, B, K, P, K, I. So we have 5 unknowns and 4 relevant equations. So it means that one of them is going to be a free parameter. Usually you have to use tabulation or dominant pole placement strategy, but I'm going to skip that and I'm going to just guess the solution because I don't want to spend too much time on it. But usually it goes on with tabulation and stuff like that, as usual, as we should do it. But I'm just going to take a shortcut here. So instead of defining omega n like this, let's basically define omega n like 0.5 and try to come up with a solution. So we will have a val double solve at a, and then b val b kp ki ki and kp. So now we can see a val and b val are positive values, which is quite nice. And their sum and multiplication are big values. It means that it would be out of the dominant region probably. And kp val is positive. Ki val is also positive. And the nice thing about kp val is that it is a low number, so it should be quite a good solution here in terms of the PI controller. So I'm happy with the solution. Again, we should use tabulation and optimize that, but I'm just going to go with it because it seems like this is a good solution, just for the sake of simplicity, of course. Now, let's define kp_val and ki_val. Now, at this point, I am going to use the PuTTY approximation, but keep in mind it's just for comparison, and I need to look at the actual system. So do we have 3 figures? Yep, nice. Hold on, grid on, title, step response of the closed loop. Now, TS PuTTY is going to be feedback fs times GS PuTTY, 1. I should, of course, be happy with this. So there should be no issue at all. And I'm just going to use figure 4, and I'm going to delete that in a moment. I'm just going to use pzmap on TS PuTTY. Let's have the step response and plot it. So let me run it. There we go. Now, before I look at that, I wanted to just to check if the solution that I came up with is a dominant one. I am doubting that you can see it, but let me show you. This is here a 0 at minus 6.75. And then we have another pole at minus 5.9 and another pole at minus 4.52, whereas the pole pair is here. And we have a 0 at the right half plane. So it seems like this is quite a good solution. I'm going to get rid of this now because this was just to check if it's a good solution or not. What you can do is you can use TS PuTTY instead of that. So we can see basically a 0 at minus 6. This is the dominant pole pair. This is at minus 4, so 8 times that, 10 times that, and then we have like 12 times that. So we have a 8 times dominance factor that is quite good for a controller design with using basically dominant pole placement. So the solution works basically. What we can do is, instead of doing that, is we could check the step info. Yes, PuTTY, and display basically the overshoot, because that's the only requirement given to us. And there we go. So it seems like we have 10.7% overshoot, which is quite nice. Now, of course, it will work with the PuTTY approximation itself, because we're already designing the controller for the PuTTY approximation. So this is what I mean by that. It doesn't make sense to look at this and conclude that the system will work, because you didn't try it on the system with delay. You're trying it on the PuTTY approximation, which you came up with, and it should work, of course, because you're using that transfer function exactly. If we are going to talk about the actual system, what you have to do is, instead of this, you should look at TS, which is going to be fs times GS. And of course, this is going to be TS. Let's give it another color. And it doesn't matter. We have to check the step info of the actual system. Now, GS times GD, I guess, because we left out that. Yeah. So we shouldn't leave that out. There we go. Let's run it again. There we go. Now we're talking. Now you can see that the overshoot value is 14%, and the step response is not that bad in terms of approximation. We could just force it to a higher order and try to basically work with that. But you can see that the actual system will never have this undershoot here because it is not the approximation itself. So just in order to check if we should stop or not, we are going to look both at the PuTTY approximation and the actual system's closed loop and compare them. But other than that, we always need to check if the actual system, the original system, works or not. Now, even if it does capture all the dynamics of the system, which we did see here, it needed a higher order one because this is the open loop. It still works for the closed loop and it works quite well. So this is refreshing to see because, well, if the response would be too off, then we need to basically increase the order until we will be satisfied with the result. If you're okay with 14% overshoot, which we should, by the way, we can just leave it at that. Some tuning methods could be to maybe aim at a lower overshoot. So maybe we could increase the zeta value a little bit, just by a little bit, to aim at 10% overshoot, or we could use the second order PuTTY approximation and have a better or more precise approximation and then work with that. Of course, it's not that difficult. You can do it. You can just copy and paste this part. And the only thing that will be different is the order will be increased. So this would be a third order one. And then you have to, of course, again, use tabulation and come up with the best solution that you can and design that. But I'm going to skip that part because I am going to introduce you to these concepts. And my aim here is to give you a basic understanding. And from that on, you can just try your best or design it yourself. So up to this point, we've seen that there's something called the PuTTY approximation, which takes out the nonlinear term, plugs in the PuTTY approximation, and from that point, you can use all the tools that you have obtained up to this point, and you can work with that. You have to be careful about the stability conclusions. You have to be careful about if the system works or not. You have to validate using the actual system. And yeah, that's basically the method that we've introduced you to. Now, there's another method, which is called the Smith predictor, which is an alternative way of dealing with systems with delay. And the nice thing about this is that it uses a special structure in order to overcome the problems of systems with delay. So let me show you how it works. Now we have the non-delay part and the delay part here. And of course, we're designing a controller. And our special structure goes as follows. Let's have our reference and then summation point. There we go. Now we take a branch out of this and we have a copy of the first branch. And here we have another summation point, whereas this is negative and this branch is positive. So we are basically taking the difference. And also, we have another branch that goes like G0, like this. Let me edit afterwards. At this point, where this is positive, of course, and this is also positive. And then we use this output. So for the feedback, like this. This will be the error. This will be control signal. And then we will have basically the whole structure here. Now, the only difference here is that in real life, this is not going to be G0 times GD. This will be called the plant itself. And we assume that the plant model is G0 times GD. So here we will have the actual system, but here we will have the model of the system. And the reason why we take the difference between the system or the plant and the model is basically the fact that this is kind of a model matching strategy. Instead of doing it with multiplication, we had before a controller that had its subpart was basically the inverse of the system, and then there were some extra dynamics that were necessary to achieve the closed loop that we had in mind. And when we had the system, and if the system and the inverse were matching each other, they would get rid of each other and we would end up in the closed loop that is desired. Here, instead of using the multiplication, we have basically the summation here. We take the difference between the system model and the actual plant. So this is basically constructed by us. And we're adding G0 back here. And then the resulting signal is going to be used in feedback. Now, if we do that, ideally, if this matches this one here, they will get rid of each other, and we will have fs g0 in the loop transfer function. So it would mean that our characteristic polynomial would look like fs times g0, and that's it. Now, we're talking about a characteristic polynomial now. If we would use directly the feedback with the system with delay, then it would have the exponential term in the characteristic polynomial, which is then not going to be a polynomial at all. But this structure, with this model matching strategy that we have here internally, we're getting rid of this delay part. We're preventing that from entering the denominator of the closed loop. So that's quite important. And this is a special structure for systems with delays, which is called Smith predictor. And it is used to get rid of this delay in the loop transfer function. Therefore, we have a proper characteristic polynomial. Now, if you look at this structure, and if I ask you what the output is or where the output is, and if you're answering that this is the output, you will be wrong. This is not the output at all. Actually, this is not even on the feed-forward path. This is on the feedback path. The only thing that is on the feed-forward path is basically this. So this is why. Because this is the plant itself, and this is the plant output. And this is going to be still remaining as the output. So all that we do is basically happening on the feedback path. And if you look closer from R to Y, that's the feed-forward path, we have Fs G0 GD. So when you write down the whole transfer function of this structure, it would be Fs times G0 times G delay divided by 1 plus Fs G0. You have to do the eliminations and the calculations, and you will end up in this closed loop here, which is interesting because this GD is pure delay in our case, and Fs times G0 divided by 1 plus Fs times G0 is basically T0. T0 being the controller and the non-delay part and the closed loop of that, because it is directly the formula that we would use if we would have a controller that is directly applied to the non-delay part. So the Smith predictor comes up with a structure so that you will use the non-delay part, you will neglect the delay part, the structure will handle delay. So you will have basically only 12 divided by s plus 4 times s plus 6, without the delay, without any body approximation. You will just use G0 to design your PI controller for 10% overshoot. Once you have done that, you will use that controller and the special structure and you're good to go. The only thing that you cannot prevent from happening is the addition of delay in the feed-forward path. And you're okay with that because there will be delay in the system. The system will react after some dead time or after some delay time. And that's not something that you can prevent at all. So you are going to be happy with that. And during the body approximation in the previous question, when we had the step response, you've seen that there's 2 seconds delay in the closed loop step response anyway. So this structure handles the delay part. You're focusing on the non-delay part, designing your controller, plug it in, and you're good to go. Of course, these advantages being simple to use and having the structure handling the delay part has a major disadvantage and drawback. Of course, it is dependent on the model. As any model matching method, this can also be thought as a model matching method. It mostly relies on the model of the system. And it is important to match the delay part exactly here. Otherwise, we will be in trouble because ideally you want to see that this branch here, this difference here, is equal to 0. So what you should do once this lesson is over, you should open up Simulink and create a structure and connect some scopes maybe here and run a simulation on that, and you will see if they are matching each other, you will get a 0 signal out of here. And this portion here is basically constructing the non-delay output, which is the predicted output without delay. It feeds that back, but the overall delay is still in the feed-forward path. Therefore, it will be delayed by 2 seconds. So the controller design is quite simple because we are not going to use any approximation. We are going to use the structure itself. When we design a controller to the system, it will look like the following. Let me just take basically this one here, or all of it, maybe, like this. And I'm going to take this one here, but I'm just using GS and nothing else. And then I'm going to use these here. Well, I could actually do something else. I don't even have to design it like this. Since we have 2 real poles, what I can do is I can just come up with the dynamic part using pole zero cancellation. Let's say 1 and 6, 1 and 0 times GS. I don't really need to convert it even into the symbolic version here. Open up a figure. Use the root locus here to come up with a gain. Once that gain is there, I can just use it like this. So let us close all. Actually, let's run 2 here. And of course, we need 10% overshoot. So S grid zeta omega n. Well, zeta is 0.59, 1/6, I guess. And let's have 1 up to 6 or 5. I'm not even bothering with designing a controller using the algebraic method. I can just use this pole zero cancellation. Seems like somewhere here, you can see 8.93. If I drag it a little bit more, 11, that's not good. So, well, 0.9. Yeah, 0.9 seems to be working. So let's say 0.9 times that should be our controller. And the only thing that we need to calculate is going to be, of course, this is not correct. I'm just going to show you the result, but you have to build this whole structure here in Simulink, basically, but I'm going to skip that part. I'm going to leave it to you. What I'm going to do is I'm just using GS, comma 1, and TS is going to be basically T0 times G delay, because I'm just adding the delay in the feed-forward path. Then I can just go ahead and take this figure here and plot it basically. And let's get this stuff here. We already have TS. So the step response, let's see. Okay, red seems to be a good color here. And I want to also see what the overshoot value is going to be. And that should be it, actually. Did we mess up stuff? Oh, yeah, it's not ls. I have to copy this part here, of course. So, yeah. Let's do it like this. There we go. Now, of course, it will go like 20 seconds, but you can see that there's a huge difference. And of course, this it doesn't have to be, but in our case, it is quite different. The reason here is that we didn't optimize the PuTTY approximation versions of the PI controller, and I just did get rid of basically a pole and then directly use the structure's advantage. Of course, they will never match each other. The Smith predictor version would be quite more powerful and be more optimizable in that case, because we are not dealing with the approximation poles and zeros. We're just dealing with the delay part with a structure, and we're extracting the non-delay part, and we're focusing on that. So it is less restricted in that case. If you have to deal with the delay part too with the PI controller, then of course you are a bit more restricted. Therefore, even if both of them will show like 10%, I can tune this a little bit so that we will get 10% overshoot. It seems like using a special structure for the delay part has an advantage over not using that and using the PuTTY approximation here. But of course, instead of having GS here, actually GD here, if you use a structure and tune the delay part, or introduce a little bit of a difference in the delay part, you will see that it will mess up. So let's conclude our discussion of today's lesson, which is about delay and dead time. You can see in the PDF we have step-by-step explanations, all the pole and zero spreads, and there's also the code which we've used to generate these plots. For the stability interval, we've used basically the root-locus plots. Here it's not 0, there's a mistake, it should be -2, as we've seen today. You can see the interval shrinks when the approximation order goes up. And we've seen it's even smaller than that. It should be 1, 5, 3, etc. And when you apply this to the system, when you apply the interval obtained by the first order approximation, you can see the actual system is not stable in that interval, whereas the PuTTY approximation, of course, is. This goes on with the second order approximation, but of course, 2.16 is a good enough value. Therefore, we have a less stable, a more unstable solution for the system, whereas the actual system is also quite bad in terms of zeta. So both of them are approximately near the j omega axis. So it's something that we can use in terms of stability interval. Now you can see there are different designs that we've introduced here, the original one, antipody approximations. If you carry out the second order pody approximation, it seems like you can increase the accuracy here, which I did skip actually in this lesson, but you can go ahead and try to do that on your own. In the PDF, I have, it seems like, chosen a different PI controller. So yeah, I didn't even design it and chose this one here. So yeah, here you can see the transfer function of this whole structure here, which you should at least try to obtain once. So you should work on that. But you can see that there's this crucial term where you can see fs times c0 e to the power of minus tau s and minus fsgm, where gm is basically the plant itself. If they are equal to each other, if gm is exactly g0 times e to the power minus e to the minus tau s, then this term will vanish. So these should match. If that's the case, you can see fg0 divided by 1 plus fg0 times e to the power of minus tau s is going to be the closed loop. And when I plotted the step response, directly used that relation, but of course that's not acceptable. I'm just showing you the end result. I'm taking a shortcut, but you should basically open up a Simulink block and place all the necessary stuff so that you can go ahead and show that the structure works. Now, here is this whole animation stuff shown. And this is basically the response in the PDF. But when you change the system a little bit, the model a little bit, the plant has, let's assume, 1.8 seconds of dead time or delay time instead of 2 seconds. And your model is not correct anymore. And when you use the structure, you end up in this interesting behavior because the delay part is a little bit off. There's a deviation. So you can see that using the Smith predictor with high accuracy delay is more advantageous. But if you are not sure about the delay portion, you might want to opt for the pody approximation because, well, at least that would work better than this one here. But if you have the exact amount of delay, and if you're sure about that, you can directly use this. Of course, this is just in the scope of our lecture, control system design lecture. You might want to construct something that estimates the delay, the amount of delay, and then you will have an adaptive system. We're not talking about that. We're just talking about offline designs. So therefore, if you have a correct model in terms of delay, you can go ahead and use the Smith predictor because it has more freedom. It's less restricted, but you can also use the pody approximation method where you will be quite more restricted due to the model and you're using the model directly without any predictor. So it will be a little bit more hard on that. So this actually concludes our lesson of today. And the next lesson will be about the frequency domain. See you then.